Hello and welcome back. In this video, we're going to continue our discussion about combining functions from the previous video. We're going to leap straight into talking about the compositions of two functions. So if we had h of x equal to 2x minus 5 and g of x equal to x squared minus 20, in addition to adding and subtracting and multiplying and dividing them, we could start taking them and plugging them into each other as inputs. Here's what that would look like. So the command that you might be given or asked to do is to compute g open circle h of x. That open circle is not multiplication. You should read that as saying composed with. So I'd say this is g composed with h of x. And if you see that, again, it's not like multiplication. It's not like you're distributing the x across this weird circle. This is saying to let g be the outside function, h be the inside function, and you're going to put h into the inputs of g. You can also say, especially when it's written this way, g of h of x is like a way that we would say it out loud. So how do you work this? Well, first, let me color code a little bit. I'm going to do g of x in pink. I'll write the outside function. So I'm going to write x squared minus 20. But instead of x, this is normally where x would be. I'm replacing x with the equation for h of x. So it's really going to be the equation for h of x that I put where I would have put the x before. In this case, it's 2x minus 5 squared minus 20. Then, almost always, there's some substantial simplification that you have to do. So let's do that. Sorry, I don't know why I thought 5 was divisible by 4. In this case, that would be my end result, because there's nothing else that has a common factor. And that's the composition of two functions. And you'll notice that it's just another parabola, but it's a different parabola. It's actually been shifted over, is a way to think about it. We can also compute this in the other order. So we might be asked to compute h of g of x. I'm going to keep the same sort of color coding scheme, but when you see h of g of x, this is saying to do the functions in this order. So in this case, h is the outside function, so I'll write 2x, I'm leaving a big space for x, I'm just writing the outside function, minus 5, because I'm going to erase that x and replace it with the equation for g of x. That's what it means to do h of g of x. And simplify some more. So in this case, the final answer is 2x squared minus 45. And one thing you should hopefully notice right away is that g composed with h and h composed with g don't necessarily give you the same result. This is not an operation that's commutative necessarily. Yeah, you just have to compute it kind of separately each time. I wrote that here. Composition is generally not commutative. F of g of x and g of f of x, sometimes you will get the same result, but only sometimes. So here's a fun math fact for you. Linear transformations, like the kind we just finished graphing in section 1.6, can actually be thought about as compositions themselves. So for example, if we were graphing y equals 2 square root of x plus 1 minus 5, which is a shift to the left, a vertical stretch, and then a move 5 units down, the graph of it looks like this. has a starting point at -1, -5, and goes up towards infinity on the right. You could actually think about this as a triple composition of three functions. I've broken this out for you. F of x could be 2x minus 5, g of x could be the square root of x, and h of x could be x plus 1. I want to challenge you to just compute f composed with g composed with h of x and see what you get. If you want to do it on your own, pause the video now. If not, I'll work it out just now. So working from the inside out, x plus 1 is the inside function. Then we take the square root of it from g, and then we do 2 times that thing that we got and take away 5, and we get 2 root x plus 1 minus 5, which is the linear transformation we started with. I will say that not all compositions result in those linear transformations. Compositions can be pretty wild, but all linear transformations of that type we did last section can be thought of as compositions of things like mx plus b, and then one single function where there's something that changes the shape of the graph in a nonlinear way. Compositions can be somewhat tricky to work out, especially if you haven't practiced them. So I would encourage you to take this example, pause the video, and work it out on your own paper. And I will work it out beneath here, and you can follow along if you get stuck. If you've worked these out correctly, both f composed with g and then g composed with f, you'll notice that you did, in fact, get the same thing both times. And not only did you get the same thing both times, you actually got x. This is a preview of something that's going to happen in section 1.8, when these two functions will become inverses of each other, or we'll consider them inverses of each other. Inverses are functions that undo the actions of one another. So you should, of course, when you do a function and then compose it with its inverse, you should get back x, which is the variable that we started with. But it's also just good practice for now for composing two functions back and forth. So now I want to talk about something a little bit technical, which is finding the domains of function compositions. And before we get too deep into the weeds here, I want to say first, as a warning, that the most important thing in this section is not this. It's what we've done before, actually computing algebraically the compositions, simplifying all those results, understanding all of that notation. If you're not sure on that, I would pause this, go do a couple practice problems, and then only come back here when you really do need to find the domains of those compositions. That said, let's get into it. I want to first look at this drawing. Sometimes it's really helpful to think about functions kind of as machines with inputs and outputs. So I have some x floating out in space, and we're talking about f composed with g of x, or f of g of x. G is the inside function, which means it's the first function that x hits when it's going through this chain of functions. X goes into g, and then whatever g does, maybe it squares it, maybe it square roots it, maybe it takes the cosine of x, I don't know. But it comes out, and we can say it's like some g of x. Then it's those results, those g of x's, that go into the function f. the function f never sees what the original x was. The function f only sees the already transformed versions of g. And then out from the function f, we get f of g of x as the final result. And that would help us think about domains. So thinking about this picture, here's how you're going to compute the domain of a composition just looking at the algebra. The first big idea. All the x's must be in the domain of g, right? You can't put something into g that wouldn't be allowed. So if g was, a square root function, square root of x, then you would need x to be greater than or equal to 0, for example. Although you could have all kinds of other things going on. Then, in addition to that, the outputs from g have to be legal to put into f. So say that f was like 1 over x. Then I would need the outputs from g to also not be equal to 0 so that I could then put them into 1 over x. It doesn't actually matter what the original domain of x was. It matters that I need g of x to satisfy the domain of f. And that's the second line. Outputs from g must be in the domain of f. So then in this little example with square root of x and 1 over x, I initially thought that x needed to be greater than or equal to 0, but since I also need 1 over root x to not equal 0, then I need x to also not equal 0. So in this case, I would say the domain should actually be the domain for f of g of x would be 0 less than x, strictly not equal to. Let's do this in another example. So say g of x is x squared minus 4. So that's the first function that x sees. I'm going to write what the domain of g is. In this case, it's all real numbers, which you can write as negative infinity to infinity. Because it's just x squared minus 4, there's no issues here. There's nothing you're going to plug in that's going to break the rules of math. But then we get our outputs g of x, and those outputs from g of x have to somehow go into f of x. So we need legal outputs from g that go into f. Well, so the domain of f of x, which is equal to root x, sorry, I'm going to clean up my notation here, is x needs to be greater than or equal to 0. The domain of the square root function is x greater than or equal to 0. But I'm not putting x's into f of x. I'm putting g of x's into f of x, right? Because I'm doing f of g of x. So really what I need to have happen is not x greater than 0. And this is that second line. I'm going to cross that out and write, I need g of x to be greater than or equal to 0. Okay. And then I know the equation for g of x, so I can say, oh, well, that would mean I need x squared minus 4 greater than or equal to 0. What? That is something called a polynomial inequality that you've maybe not solved before. Why don't we just solve this by thinking about the graph? X squared minus 4 is, of course, a parabola. Minus 4 would be it's shifting down. And since it goes over 2 and up 4, conveniently, it would have zeros at 2 and minus 2. So x squared minus 4 is greater than 0 on the interval negative infinity up to negative 2, greater than or equal to, so we'll do bracket union 2 to infinity. Just that kind of double-ended interval. That will also be part of the domain of f over g, or f composed with g, sorry. So the domain of f composed with g, up here at the top, is the union, or sorry, the intersection of those two things. So we had the domain of g was negative infinity to infinity. The domain of f composed with g is negative infinity up to negative 2, bracket, union, bracket, to infinity. It's a little technical. It's kind of tricky, but this is a weird graph. let me show you the graph of this function, and then maybe you can get a sense of how it might be helpful to have computed that domain before trying to make the graph. Here's what this function looks like. This is the square root of x squared minus 4. And there is, in fact, nothing down here. This function is just in two pieces, one piece going off to the right and another piece going off to the left in a happy sort of linear way. And in between, there's just absolutely nothing, because this area where there's nothing from -2 to 2 is the place where x squared minus 4, just the inside part, was less than 0. And so you couldn't take the square root of it. But that's an example of how computing the domain of a composition before trying to graph the composition can help you understand what's going on better in the function itself. Let's do another example. So this one is made of two rational functions, 2 over x minus 1 and 3 over x. First, we're going to find the domain of f composed with g of x. So I need to find the domain of f. Actually, I'm going to do the inside first. So I'm going to find the domain of g. G of x is 3 over x. So the domain will be x not equal to 0. It'll be all real numbers except x should not be 0. And then the domain of f, which is 2 over x minus 1, is, well, I need the denominator to not equal 0, so I need x to not equal 1. But before I box that in, I need to remember that in my little diagram, I'm not actually putting x's into f of x, I'm putting g of x's into f of x before I can get the output. So instead of x not equal to 1, what I'll actually write is g of x not equal to 1. That would be sort of the correct domain when you do it in the composition. And that tells us what equation to set up. I know the equation for g of x, it's 3 over x. I can say, what would make that not equal to 1? Let's multiply by x on both sides. You can do that, and you get 3 is not equal to x. So I actually have a domain where I need x to not be 0. I need x to not be 3. I don't actually care. I know I wrote x not equal 1, but I was actually meaning I need g of x to not equal 1. So x equals 1 is totally fine in the domain. So then if we write out what the domain kind of should be, we need x to be a real number. But x should not be 0, and x should not be 3. And we don't care about the g of x not equal 1 part, because all that really served was to tell us that x itself should not be 3. So that's how you could do this in, say, set builder notation. But you could also write it in interval notation like this, using unions to exclude the 0, and unions to exclude the 3. Let's now see if we can just find and look at the composition itself and see if there's another way that we can perhaps have found those domains in this problem. So we're going to find and simplify f of g of x. So I'll start by writing the equation kind of for f of x, which is 2 over x minus 1. But I will replace what I had with x with the equation for g, which is 3 over x. And I'm just going to try to simplify that out a little bit. So 2 over 3 over x. Right away, I can see that I'll have the excluded value, that x should not be 0. Just standard excluded value stuff. Then I'm going to use everything I know from, I think, section p.6. We'll take this 1 over 1 and multiply it by x over x to get a common denominator. Just that single term, you're just multiplying it by 1. So then you'd get something like 2 over 3 over x minus x over x, which would give you 2 over 3 minus x over x, which if we come over here, would give you 2 over 3, what do you think of this as 2 over 1? Because I have the biggest fraction bar, so this is like 2 over 1 times x over 3 minus x, and I can now see from this part that I also need x to not be 3. And those were the two excluded values from the domain earlier. So then the final answer would be something like 2x over 3 minus x as a final composition simplified. And that's another way you can find the domains of a composition, is actually just compute the composition and inspect the equation you get using everything you know about finding domain. That said, you won't always have the equations of both functions. In the broader land of mathematical theory, you don't always know what the equations are. Sometimes you do have to deal with them in that more theoretical way like we were doing earlier. So it's important to understand that as well. This mental image of a chain of functions connecting together, any number of functions, is really, really powerful. And I strongly encourage you to do as much as you can to really start to think about function composition in this way. The last topic here is decomposition of functions, and it also has to do with this idea of a chain of more, 2 or more functions. That's why I have a little picture of a chain here. So it's kind of like just the reverse of composing functions. Say you have some h of x and you're given its equation. One common thing you might like to do is find some f and g so that h of x is the composition of f and g together. So, f composed with g. When you do this, it helps to think about like what's going to be the outside function and what's going to be the inside function. Now, if I'm inspecting h of x, I could actually recognize like a couple different options for what would be the outside function and the inside function. So I could say that an inside function could be x minus 3, right? X minus 3 is a function. Then the outside function is everything else that happens to the x minus 3. So in this case, my option, my result would be g of x, the inside function, is x minus 3, and then f of x would be something like 2x squared plus 1. And then you could check this by doing, whatever you wrote. You could do f of g of x. And if my g of x is x minus 3, I would square it, multiply it by 2, and add 1, and that's the same as the h of x. And that's all decomposition is saying pick an inside function and an outside function and write them separately. What's fun about decomposing functions, and I actually really enjoy doing it, is you can have many options for what your inside and outside functions are. So for example, I could have also said, let my outside function be x minus 3 quantity squared, or sorry, I said outside, inside function. Let my g of x be the whole parabola part, x minus 3 squared. Then the outside function is the function that would multiply that by 2 and add 1. So then the f of x would be 2x plus 1. And you could check by composing those back together. F of g of x, you would start with g, x minus 3 squared, multiply it by 2, and add 1. And you do get back that original. So decomposing functions, really nice. It's actually really nice to be able to decompose functions in multiple ways. Something that really helps in calculus when you're taking apart a function, you can work with each part separately if you're finding things like rates of change, and then put them back together in a much more simple way. Well, folks, I hope you've enjoyed this video on compositions of functions. We've done a lot. There's a lot of theory. Remember what I said before, which is that the most important thing is understanding the basic algebra and notation of composition. And then the domain stuff will follow after you practice all of that and really get that locked down. Let me know what questions you have. Good luck on your homework, and I'll see you all next time.